Let's look at some applications of vectors, and we'll start with displacement and velocity, including relative velocity. Now, distance and displacement, the first thing you should think about is that distance is a scalar quantity. It's a measure of how far an object has travelled. It doesn't take direction into account. So distance is scalar. In contrast, displacement is the vector quantity. So it's a change in an object's position from its starting point to its finishing point. It consists of both magnitude and direction. Now, just as an example, if I travel from here to school and then back home again, I may have travelled a distance of 6 kilometres. 3 kilometres to school, 3 kilometres back home. My displacement though is 0 because I'm back where I started. So that's the best way to think about it. So I'm going 3 kilometres in one direction, coming back in the opposite direction. So 3 take 3 is 0. So thinking about that, distance is going to be the magnitude of vector A plus the magnitude of vector B. In contrast, displacement, which we might call vector C, is going to be vector A plus vector B. So if we look at the diagram here, we have vector A and we have vector B. So our displacement is this vector C. And note that that vector C has magnitude C and direction theta. So let's look at an example. Harrison embarks on a journey with 3 separate parts. First he travels 12 kilometres north, then he travels 9 kilometres east, and finally he travels 2 kilometres south. Use a vector technique to calculate distance and displacement from his starting point. So we have a Cartesian plane here to make it a very accurate depiction of what's happening. So first of all, he went 12 kilometres north. You should use a ruler. I'll put that this is his starting point. I'm going to label that vector A. He then travelled 9 kilometres east. I'm going to label that vector B. And finally he travelled 2 kilometres south, and I'm going to label that vector C. So this here is the finish. Now to calculate distance, nice and straightforward. Distance is going to equal 12 plus 9 plus 2, which is 23 kilometres. Now for displacement, what I actually need is this resultant vector here. Now there are 2 ways of doing this. You can do it with a diagram, which is quite straightforward to do, but I'm going to show you the vector technique first. So I can write my A is equal to 12j, my B is equal to 9i, and my C is equal to negative 2j. So they're my vectors. So that means my displacement is going to be 12j plus 9i take 2j, which is 9I plus 10J. Now the magnitude of the displacement is going to be the square root of 9 squared plus 10 squared. That's the square root of 181, which is approximately 13.45 kilometers. Now my angle is going to be inverse tan of my y over my x, opposite over hypotenuse, which is inverse tan of 10 over 9, which is approximately 48.01 degrees. Now, can I check this? We're looking at the diagram. This is my resultant. I can also get it with vector 9I and 10J. So R equals 9I plus 10J, which we'll see matches my displacement. The angle theta is this angle here, which is my opposite over my adjacent. Now if we want to work out, now it doesn't actually ask for bearing either, I just read the question. Use a vector technique to calculate Harrison's total distance and displacement from his starting point. So I've actually worked out too much. But anyway, so this here is 48.01 degrees. If we wanted the bearing though, we would work out 90 minus 48.01, which is approximately 41.98 degrees. Finish with the therefore statement. So Harrison travels a distance of 23 kilometres. His displacement from the starting point is approximately 13.45 kilometres. And in red, because we worked it out, I put his bearing as approximately 42 degrees true. Not required though.